Good morning, all of you. My name is Annu from BSc Chemistry Honors final year. Today, my topic is hard and soft acids and bases. The term acids and bases are routinely used in our daily life. Chemists have been classifying substances as acids and bases since long time. Lavoisier noted that a common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius developed the theory of acids and bases known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions in aqueous solution, and a base is a substance which gives hydroxyl ions in aqueous solution. The strength of an acid or base depends upon its capacity to provide H positive and OH negative ions, respectively. The process of neutralization of an acid by base can be represented by the reaction H positive plus OH negative gives H2O. In 1923, J.N. Bronsted and T.M. Lowry independently proposed a new acid-base theory. According to their theory, an acid is a proton donor whereas a base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. In 1923, J.N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor, while base is an electron pair donor. The earlier definitions of acid and bases were solely based upon the observable properties such as taste, ability to dissolve substances soluble in water, and their effect on vegetable dyes. The term acid was applied to the substances that have a sharp or sour taste, turn blue, litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to the substances that have a bitter taste, so freely turns red, litmus blue. However, tasting and feeling chemicals are dangerous methods of determining whether the substance is an acid or base. You should never taste or touch solutions of chemicals in laboratory. There are, however, other methods of recognize acids and bases. For example, acid and bases change the color of the certain dyes. One of the most common indicator is a vegetable dye obtained from the known as litmus. Aqueous solution of acids turn the litmus red, whereas aqueous solutions of bases turn it blue. Thus, any substance which has unshaded pair of electron can act as Lewis base, whereas a substance which connects empty orbital to accommodate a pair of electrons act as Lewis acid. In other words, substance capable of donating a pair of electrons is regarded as Lewis base, and substances capable of accepting a pair of electrons are regarded as Lewis based acids. Acid base or neutralization reaction may be regarded as donor acceptor reactions or coordinate covalent bond formation reaction. The classical example of Lewis acid base reaction is that between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is Lewis acid and ammonia is a Lewis base. Lewis concept of acid and base is very commonly used because of its simplicity and the ease with the formation of the coordination compound can be explained. In brief, all the usual ligands can be regarded as Lewis base, whereas all the metals ion can be regarded as Lewis acid. The degree of affinity of a metal ion for ligands can be termed as Lewis acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. Hard and soft acids and bases. An acid-base reaction, according to Lewis concept, involves the reaction between a donor A and acceptor B as formed complex given as A plus B is A ratio B. The formation of the stable complex between the donor A and acceptor B depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive, and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive, and Pt4 positive. Based upon the preferential bonding, the acid and bases have been classified into two groups, that is class A and class B, according to their preference. Class A metal ion includes Class A metal ion includes alkali metals, alkaline earth metals, lighter and more highly charged ions. For example, Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, etc. Hydrogen ion H positive. Class B metal ions include heavier transition metals of second and third transition series, that is Cd2 positive, Hg2 positive, Pd2 positive, Pt2 positive. Heavier transition metals in lower oxidation state, that is Hg positive, Hg2 positive, Cu positive. Lower valent metal ions such as zero valent metal in metal carbonyls, depending upon the type of metal ions, ligands can be classified as class A or class B depending upon their preference. Class A ligands include molecules or ion with donor atoms and nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class A ligands prefer to form strong complexes with the class A metals. Class B ligands include molecules ion with the donor atoms, phosphorus, arsenic, sulfur, selenium, iodine, etc. Class B ligands prefer to form complexes with Class B metal ions. It was in 1963 Pearson coined the term hard and soft acids and bases for Class A and Class B metal ions and ligands respectively. According, Class A metal ions are referred to hard acids, while Class B metal ions are called soft acids. Similarly, Class A ligands are named as hard bases, whereas Class B ligands are termed as soft bases. In summary, according to Pearson, Class A acids are hard acids, Class B acids are soft acids, Class A bases are hard bases, and Class B bases are soft bases. Classification of acid and bases and as hard and soft. Pearson observed that it is possible to correlate acid and base interaction on the basis of hard and soft acid and bases. He observed that type A metal ions, that is acids, were small, compact and not very polarizable, and these preferred ligands, that is bases, that were also small and less polarizable. He called these acids and bases are as hard. On the other hand, the type B metal ions and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed that hard acids prefer hard bases and soft acids prefer soft bases. Classification of acids. A general classification of some common acids and hard acids along with some borderline cases is given in table 4.1. Hard acids H positive, Li positive, Na positive, K positive, Be2 positive, Mg2 positive, Ca2 positive, Cr2 positive, Al3 positive, and so on up to HX, H bonding molecules. Soft acids Cu2 positive, Ag positive, U positive, Tl positive, Hg positive, Pt positive, Cd positive, so on up to CH2 carbons. Borderline acid Fe2 positive, CO2 positive, Ni2 positive, Cu2 positive, Zn2 positive, Sp3 positive, so on up to Pb2 positive. As inspection of table 4.1 reveals that hard acids usually have the following characteristics. First, hard acids are cations of smaller size or lighter elements. Hard acids are cations of higher oxidation state. Hard acids are molecules cations with lesser number of valence electron. Hard acids hold the valence electron tightly and consequently are not easily polarizable. In summary, hard acids binds strongly to the proton. Hard acids are small size, compact, are not easily polarized. A close look at table 4.1 also reveals the soft acids possesses the following characteristics. Soft acids are cations of the larger size or heavier elements. Soft acids are cations of lower charge. Soft acids are molecule ions with large number of valence electrons. Soft acids do not hold the valence electrons tightly, are therefore easily polarizable. In summary, soft acids are large sized and easily polarizable ions molecules that bind strongly to the highly polarizable ion molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither hard or nor soft are called borderline acids, which are shown as the extreme right on the table 4.1. Borderline acids have properties which are intermediate between that of the hard and hard base. In case of borderline acids, the properties such as size, oxidation state, and polarizability of the cation molecule are neither too low or nor too high. On the other hand, soft acids will show the opposite trend to and the following order of preference of the binding the donor atoms ions within a group is observed. Iodine much greater than bromine, greater than chlorine, greater than R2Te, greater than R2Ce, and so on up to R3N. The above trend can be pictorially represented as complex of type metal ligands. Complex of type metal is strongest to weakest, weakest to strongest. Question 4.1. What type of interaction do you accept between a hard acid and a hard base? Since both hard acid and hard bases are not easily polarizable, their interactions are predominantly ionic. Question 4.2. What type of interaction do you accept between a soft acid and a soft base? Since both soft acid and soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases is generally classification of some commonly used ligands into hard and soft bases with borderline bases is present in table 4.2. Hard bases F negative, Cl negative, NH3, RNH2, N2H4, so on up to RL chi. Soft bases H negative, R negative, iodine negative, so on up to R3As. Borderline bases Br negative, C5H5, and so on up to R and C. A Gallons at the table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the proton. Hard bases contain donor atoms of high electronegativity. The donor atoms in hard bases possesses low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbitals of high energy. In summary, hard bases bind strongly to a proton. The donor atom in the case of hard bases is of high electronegativity and low polarizability. A further inspection of table 4.2 reveals that the following features are observed in case of soft bases. Soft bases contain donor atoms of low electronegativity. Soft base contains donor atoms of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low lying energy orbitals. In brief, soft bases contain less electronegativity known metals. The donor atoms in such bases possesses donor atoms. They are easily polarized, just as three borderline acids. There are borderline bases also. Properties of borderline bases are in between those of soft and hard bases. It is important to note that categories are not a signifying divide. For example, halide ion form a series from the very hard fluoride ion through the hard borderline chloride ion in the borderline bromide ion and soft iodide ion. These soft acids also known as class B metal ions, the group of metal ions and that are in lower in the portion of metallic elements shown in figure 4.1. Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compound between acids and bases. This rule is quite often named as HSAB principle. According to this principle, hard acids prefer to bond with hard bases while soft acids prefer to soft bases. It is important to note that the hardness and softness of acid and bases refers only a hard and soft interactions. This is by no means related to the strength of acid and bases. For example, both F negative and OH negative ions are hard bases, but the basic strength of OH negative ion is similar to 10 raised to power 13 times that of fluoride ion. In other words, hard acids will show the following order of preference of binding of donor atom: fluorine negative greater than, so on up to R3SB. Applications of HSAB principle. Pearson principle of HSAB has a number of applications in inorganic chemistry. Some of these discuss below. First, stability of the complexes. We have already noted that hardness and softness of acids and bases are related only to the hard and soft interaction. Hardness and softness of acids and bases have nothing to do with inherent acidic or basic strength of the acids and bases. For example, both OH and F negative ions are hard bases, although OH ion is for stronger a base than fluoride ion. In fact, OH ion is 10 base to power 13 times more stronger than base of fluoride ion. A plus B gives a ratio B. The complex AB will be the most stable if A and B are either both hard and both soft. The complex AB will be least stable if A is hard and B is the soft, or A is soft and B is hard. For example, a complex between a soft acid Ag positive and soft base iodine negative ion is quite stable, in contrast to the one between a soft acid Ag positive and hard base F negative gives Az positive plus 2I negative gives AzI2 negative. Soft interactions: Az positive plus 2F negative gives AgF2 negative. Soft hard interaction. Similarly, the reaction between LiI and CSF, resulting in the formation of LiF and CSI constitute an interesting example suggesting the preferential stability of soft and hard combination. Some of the other important reactions suggesting the stability of soft and hard interactions are given below. CuI2 hard soft plus CuF soft hard gives CuF2 hard and plus 2 CuI soft. Exercise why COF6 whole 3 negative complex is more stable than COI6 whole 3 negative. Solution: in both the complexes COF6 3 negative and COI6 3 negative, the oxidation state of cobalt is +3. Cobalt 3 positive is an hard acid, therefore its combination with the hard base, that is fluoride ion, will lead to which is hard interaction. On the other hand, combination of CO3 positive with the soft base iodine will lead to the hard soft interaction. So most COF6 whole 3 negative is more stable than COI6 3 negative. Second, classification of acids and bases. The acids and bases can be classified as a hard or soft depending upon their preference for hard and soft reactants. We have already know that H positive is a hard acid, whereas CH3Hg positive is a soft acid. If B happens to be hard base, the reaction on the left hand side will be preferred. NH4 positive plus CH3H positive gives arrow CH3Hg positive NH3 plus H positive, which means the formation of NH4 positive is preferred because of hard acid H positive and hard base NH3. On the other hand, if B is a soft base like R2S, the right hand side reaction will be favored as shown. R2SH positive plus CH3Hg positive, forward arrow CH3Hg SR2 plus H positive, which means the formation of a CH3Hg SR2 is preferred because of soft acid H3 Hg positive and a soft base SR2. Similarly, an acid can be classified as hard or soft depending upon the direction of equilibrium. We know F negative is a hard base and SCN is a soft base. If A is a soft acid like Ag positive, then the above reaction is forward direction is favored. Conceptually, AgSCN is formed through soft interactions, hence according to HSAB theory, the reaction is preferred in the forward direction. On the other hand, if A happens to be the hard acids, then the forward reaction is not favored, rather the backward direction is preferred. Conceptually, NAF is formed through hard interactions, thus according to HSAB theory, the reaction is preferred in the backward direction. OH is much stronger base than SO2 3 negative and hence can't be displayed by weaker base and SO3 2 negative. This reaction, however, is favored by HSAB principle. CH3CdOH soft plus CO3 SO3 2 negative soft equilibrium CH3CdSO3 negative soft plus OH negative hard. It is important to conclude at this stage that Lewis acids, Lewis base reactions are governed by two independent principles, that is strength of acid or base, second softness and hardness of acid and bases. The definition of hardness primarily used the idea of polarizability, which states that a less polarizable species is hard and a more easily polarized is soft. For ions of similar charges, the ratio of the charge of radius should be used to assesses the relative polarizability, or however HSAB principle does not make into consideration the quantitative idea of relative hardness or softness of the species. In summary, major limitations of HSAB principle are: first, HSAB principle is too general and without any qualitative scale of measurement. Second, HSAB principle does not take into consideration the acidic or basic character of the compounds. Third, HSAB principle fails to explain the feasibility of the reaction. Limitations of HSAB principle: the hardness and softness of an acid or base is primarily related to the stability of the hard and soft interaction. It is no concern with the acidity or basicity of the acid or base. For example, OH and negative and F negative are well known hard bases. However, the basicity of hydroxide ion is very large as compared to fluoride ion. A strong acid is well known to displace a weak acid. For example, the reaction between a sulfite ion and hydrogen fluoride ion proceeds in the forward direction. It means that the stronger base SO3 2 negative can easily displace the weaker base F negative ion from the acid hydrogen fluoride. Similarly, a strong base can displace a weak base from a soft acid methyl mercury cation. However, the above reaction is also not favored according to HSP principle, which only favors hard or soft interaction. In both the above cases, it is inherent strength of acids or bases this that force the interactions in the forward direction in spite of the less preferred formation of hard soft pairs in the product. In other words, significant different bases strengths forces the reactions against the wishes of hard soft interaction. However, then when both the strength of acids and bases and hardness softness are significantly different, when HSB principle works well, resulting in work products having hard and soft combinations. Symbiosis. The hardness or softness of an acidic or basic center is not an inherent property of an atom but depends upon the substituents. Thus, ammonia is a hard base while pyridine is a borderline base. The acidic B3 positive ion is a borderline between a hard and soft acid. Addition of three small sized non-polarizable substituents like fluoride ion make it a hard Lewis acid BF3, whereas addition of electron donor and easily polarizable group like hydride ion make it a soft Lewis acid, that is BH3. Jorgensen observed that hard ligands have a tendency to combine with metal ion, having hard ligands, and soft ligands have a tendency to combine with the metal ion already having soft ligands. He coined the term symbiosis for such interactions. The hard BF3 molecule prefers to combine with hard base to form tetrafluoroborate BF4 negative, whereas soft acid BH3 prefers to combine with soft base H negative to give tetrahydroborate BH4 negative. An important outcome of symbiosis is the symmetrical substituent compounds are formed in presence of the unsymmetrical substituted compounds. For example, compounds containing mixed substituents interact strongly to yield symmetrical compounds with the same substituents as given below. BH3F negative soft hard plus BF3H negative hard soft gives BH4 soft plus BF4 negative hard. In brief, symbiosis may be defined as the tendency of soft ligands to combine with the metal ion already having soft ligands and the tendency of hard ligands to combine with the metal ion already having hard ligands. Theoretical basis of hardness and softness HSB principle. First, electrostatic interaction theory. According to this theory, hard acid and hard base form purely ionic compounds. We know that the electrostatic energy of an ion pair is inversely proportional to the interatomic distance. It means the smaller the ions, the smaller will be internuclear distance and hence greater will be the electrostatic energy between the ions. As a result, the final compound formed by hard acid and hard base will be highly stable. Polarizing power and polarizability. Electrostatic interactions can't explain the soft interactions because of the bigger size of the soft ions. Therefore, the interaction between large sized acid and base must involve covalent character. For example, soft acids such as Ag positive, Hg positive, etc. form strong compounds with soft base like S2 negative, I negative, which has substantial covalent character. It is these d electrons that have more polarizing power. Secondly, the soft bases like S2 negative and I negative are easily polarizable, thus bonding between soft acid and soft base is largely covalent. Third, natural occurrence of ores and minerals. The natural occurrence of ores of certain metals can be easily explained on the basis of HSB principle. Hard acid metals ions such as Mg2 positive, Ca2 positive, Al3 positive, etc. frequently occur as their oxides, fluoride, chlorides, and carbonates. This is primarily due to their preferred hard hard base interaction. We know that oxides, halides, and carbonates are all hard base. These hard acid metals ion can't occur as sulfide because S2 negative is a soft base and can't form stable compounds. The electronegativity value A of this atom is similar to the Pauling of Allard-Rothko, and the parameter B is called charge coefficient. Small, hard, and non-polarizable atoms have higher value of B, whereas large, soft, and polarizable atoms have smaller value of V. Parr and Pearson introduced a new term called absolute hardness for neutral as well as charge species and correlated it with absolute electronegativity. The absolute hardness is defined as one half the difference between the ionization energy energy, and the electron affinity. Neta is equal to I minus A by 2, where I is ionization energy, A is electron affinity of a species in the question. We know Mulliken definition of electronegativity is kappa is equal to 1 plus A by 2. Hardness of base and acid may be given as neta B is equal to neta species B positive is equal to half IB positive plus AB positive. Neta is equal to neta species A is equal to half bracket IA minus AA. In order to understand as Y is equation 4.6, the base B is represented as B positive, wherein equation 4.7 acid A is represented as such as A. Let us consider the interaction of acid A and base to form combined compound AB. A plus B gives A ratio B. In the formation of the compound AB, electrons will move from AB to A, which is indicated by partial positive and partial negative charge. Hardness of B refers to species going from partial positive to partial 1 plus positive charge, while hardness A refers to species ionization from partial negative to charge 1 plus partial negative. If the shift of the charge partial is taken as equal to 0.5, then the charge one becomes B is 1.5 and A becomes 0.5. That justifies the reason why species B is shown as B positive and A is neutral equation. A close inspection of the table 4.4 4.5 reveals that the absolute hardness values are in good agreement with their known chemical behavior. Hydrogen is the only exception which is different in all three tables. It is advisable to consider it as a special case. With the exception of H negative, the values of hardness parameters of all other bases are accepted. These hard bases F negative and OH negative have larger value of neta B, while the soft bases SH negative and CH3 negative has smaller values. The hard acids such as Na positive, Mg2 positive, Al3 positive has large neta A value, whereas the soft acids such as Az positive, Cu positive, Au positive has small neta A values. Borderline metals ions such as Mn2 positive, Fe2 positive have intermediate values. It is interesting to note that down a column in the periodic table from Mg2 positive to Ba2 positive, there is steady increase in the softness. Similarly, observation of softness is made in going from nickel to positive to Pd2 negative. There is also an accepted increase in the hardness values with increase in the oxidation state. The neta value of Tl3 positive suggests it to the harder acids, where Tl3 positive is well known as to be chemically softer. However, a comparison of Tl3 positive with the other trivalent ions show the accepted soft character. Soft acids are generally transition metals in low oxidation state containing loosely held d electrons. These electrons can be easily donated to ligands. On the other hand, soft bases are pi bond acceptors such as CO phosphines, R3p alkenes, alkynes. In soft acid base interactions, pi bonding is very important. Sigma bond formation due to the donation of electrons from the base to the metal is reinforced by pi back donation from the metal to the base. 4.9 Relation to molecular orbital theory. Molecular orbital theory is a powerful tool for explaining structure and bonding, visible UV spectra and detailed mechanism of chemical reaction. The concept of absolute electronegativity and hardness can be also explained by using molecular orbital theory. The ionization energy is a measure of the energy of the highest occupied molecular orbital, HOMO, where the electron affinity is a measure to the energy of lowest unoccupied molecular orbital, LUMO, with the change in sign of given molecule. According to Koopman theory, E homo is equal to minus I, E LUMO is equal to minus E. The hardness and softness depend upon the average gap between the HOMO and LUMO. The combination of soft acid and soft base is analogous to the situation in which LUMO of Lewis acids has about the same energy as HOMO of the Lewis base. The combination of the orbitals result in the greatly reduced energy for the electron pair coming for the table for this base, thus giving a strong covalent bond. For the hard acid and hard base, there is a greater mismatch of HOMO and LUMO energy, so that there is a little energy advantage is to be granted for the orbital interactions. Complete. Thank you.